In the previous lesson, we evaluated double integrals over rectangular regions. We can also evaluate double integrals not only over rectangles but over a general region. In particular, this region here is what we call a type 1 region. We define type 1 region as a region on the plane or a set of ordered pairs where x is bounded by lines x is equal to a and x is equal to b, and y has a lower bound y is equal to h of x, and an upper bound y is equal to g of x. In the three-dimensional space, this is the solid under the graph of f of x, y over a type 1 region. Here, the region is labeled R. The volume of this solid is the double integral of f of x, y with respect to dy dx. The order is strictly dy dx, whose bounds in y are h of x and g of x. As seen in our drawing, the lower bound is h of x and the upper bound is g of x. And the bound of x is from a to b. The important details here are the bounds and the operator. Note that the bounds of y are functions in x. It can be a constant, but if it is a function, then it should be in terms of x alone. Another important detail is that the order of integration is dy dx and not dx dy. For our first example, let's evaluate the double integral of 2x minus y over the region R, where the region is enclosed by y is equal to x squared and x is equal to y squared. Let us observe first how is a double integral written here. The operator dA means either dx dy or dy dx. While the double integral here, sub R, means that we are integrating over the region R. Thus here in this example, we are still to find the bounds for x and y. When the bounds are not explicitly given, it is essential to draw the region on the plane. So let's start in our example. First, let us draw y is equal to x squared. We start with a dotted graph first and do the same with x is equal to y squared. The region enclosed by these two curves is given by this one. Second step is to draw vertical strips. And the g of x here, or the upper integration bound for y, is the upper boundary of the strips. And h of x, or the lower integration bound for y, is the lower boundary of the strips. So in our example, the upper boundary is x is equal to y squared, and the lower boundary is the red one, y is equal to x squared. Recall that our boundaries of y must be functions in terms of x. Y is equal to x squared is already good as our lower boundary, but for x is equal to y squared, we still have to solve for y, so that would be y is equal to plus minus square root of x. But since we are in quadrant 1, then y is always positive, so we get y is equal to positive square root of x. On the other hand, for the boundaries of x, just look at the intersection points of the two curves. We get x is equal to 0 and x is equal to 1. Once we identify the bounds in our graph, then we can now write these details in our double integral. First, the order of integration is dy dx since we are dealing with a type 1 region. So the inner integral integrates with respect to y. So the inner bounds are square root of x, that is the upper bound of y, and the lower bound is x squared. While the outer integration bounds are x is equal to 0 and x is equal to 1. We now have the integration bounds and the order of integration, so we can now integrate. The integral of 2x with respect to y is 2xy minus the integral of y, that is y squared over 2. Then evaluate this from x squared to square root of x. First, evaluate at square root of x. We have 2x raised to 3 over 2 minus the square of the square root, so we get minus x over 2, minus evaluate it at x squared, so we have minus 2x cubed minus x raised to 4 over 2. Instead of simplifying this, let's just integrate as is with respect to x. So the first term, we have x raised to 3 over 2. If we integrate it with respect to x, that would be 2x raised to 5 over 2 all over the new exponent 5 halves. For the second term, we have negative x squared over 4 minus 2x raised to 4 over 4 For the last term, note that we have minus negative. So we write here plus. Then integrate. We have x raised to 5 over 10. And evaluate this from 0 to 1. There is no need to evaluate at 0 since we will just get 0. If we evaluate at 1, we have 4 over 5 minus 1/4 minus 2/4 plus 1 over 10. Then simplify, we get 3 over 20. For our next example, let us consider this double integral of y e raised to x minus 1 squared dx dy. You might think that cool, bounds are given, but take note that the order of integration is dx dy, which is not the order of integration of type 1 regions. Consequently, because of that, the inner bounds are bounds of x instead of bounds of y. This is actually what we call the type 2 region, which we will discuss in our next lesson. But let us try to answer this one. Let us integrate with respect to x first. Here we have an inner function, so we let u be x minus 1 squared, which gives us du is equal to 2 times x minus 1 dx. But this value of du is not present in the integrand. Therefore, we won't be able to use integration by substitution here. Thus, what we will do is we will change the order of integration from dx dy to dy dx. And for us to get the correct bounds for x and y, it is essential to draw the region. So let's get first the given bounds. From here we have y is equal to 0, y is equal to 2, x is equal to 1 plus y squared, and x is equal to 5. With these given bounds, we get this type 1 region here. The upper boundary of the vertical strips is 1 plus y squared. We want it to be a boundary of y, so we solve for y. We have plus minus square root of x minus 1. But we are in quadrant 1, so we get positive square root of x minus 1. On the other hand, the lower bound is given by the x-axis, or y is equal to 0. For the bounds of x, you can see clearly from the graph that x is from 1 to 5. So when we rewrite the double integral, the order will now be dy dx. The upper bound for y is square root of x minus 1, lower bound is 0, and the bound for x is 1 to 5. Before we continue, just a side note that the bounds are not simply interchanged. So interchanging the order of integration in type 1 regions is not as simple compared with rectangular regions, where we can use the Fubini's theorem. Going back, we now integrate y. The integral of y is y squared over 2. And when we evaluate it from 0 to square root of x minus 1, we obtain x minus 1 over 2. And now that our integrand is in terms of x alone, we now let u to be the exponent of e, u be equal to the square of x minus 1. So du is equal to 2 times x minus 1 dx. Moreover, the bounds for x, which is from 1 to 5, will be changed to the bounds of u, which is from 0 to 16. So when we rewrite the integral, we have the integral from 0 to 16 of e raised to u times 1/2 times 1/2 du, or simply 1/4 du. We can copy the coefficient 1/4 and integrate e raised to u. Recall that the derivative of e raised to u is itself. Therefore, its antiderivative is also itself. We now evaluate from 0 to 16. Take note that e raised to 0 is equal to 1. Thus, our final answer is e raised to 16 minus 1 all over 4.